We talked before about different data types, in particular this uint8 or unsigned integer 8-bit quantity. Let's just have a little bit of a look at numeric values. So I'm going to do a really trivial example here. I'm going to create a variable called a, which is equal to 100, a variable b, which is equal to 200. You can do some really simple arithmetic and you can work out what the answers are going to be. A plus b is 300, a minus b is minus 100, a divided by b is equal to 0.5. Or exactly as we would expect. These numeric quantities within MATLAB are double precision numbers. Let's remove these variables from the workspace. They're all gone. And I'm going to create variables now of the uint8 type. So this variable a, we can see, is of the uint8 type, and it's got a value of 100, just like before, but the type is different. Here we create the variable b. It's got a value of 200, and it's of the uint8 type. So now let's do some arithmetic. Let's add a and b together. It's got a value of 255. Subtract them, and we see that the value is 0. Now let's do a division. So these answers are a little bit surprising, and the reason for this is that the unsigned integer 8-bit numbers have got a very limited dynamic range. So the results that we see here on our screen make perfect sense. I add the two numbers together, and although the result should be 300, the maximum possible value that it can have as a uint8 type is 255, and that's what MATLAB has set it to. Similarly, the smallest possible value it can have is 0. So although the correct result was minus 100, MATLAB has set the answer to 0. Well, we call it clipping. So the results are being clipped. They cannot go below 0 and they cannot go above 255. The division result is also a little bit surprising. What has happened here is that a divided by b, the result is 0.5, and MATLAB has rounded that up to the value of 1. In many programming languages, if I divide a small integer by a larger integer, the result will be 0. MATLAB has done a rounding operation and given a value of 1. In terms of the actual computer hardware, the uint8 type is stored in a single byte of the computer's memory. The smallest value is when all of the 8 bits have got a value of 0, equivalent to a decimal value of 10, and the largest value is when all of the bits have got a value of 1, which is equivalent to the decimal value of 255. For an arbitrary n-bit integer, the maximum value is 2 to the n minus 1. MATLAB supports a number of additional unsigned integer types. It supports a uint16, which has got 16 bits, and a uint32, which has got 32 bits, and these are able to represent numbers with much larger maximum values. Now, we've displayed this image before, and as previously discussed, the pixels in this image are of the type unsigned integer. We click around and here we have the integer values of the pixels. The brightest one will be 255, the smallest one will be 0. Now there's another way we can represent the pixels in an image, and I'm going to create a new variable. I'm going to call it imd, image double. And what we're going to do is we're going to read the image in again, but into a different variable this time. We're going to pass the option double. Now what this will do, convert all of the pixels into double precision numbers instead of unsigned integer numbers. Now let's display this new image, and I'll create a new figure, and I will display my new image in this new figure. Now we see it looks exactly the same as the other one, but if I click around on the pixel values here, we'll see that they're floating point numbers now. And in this convention, 0 represents black and 1 represents white. So this is a reasonably bright number. In the dark of this doorway, the pixel values are only 0.03. So this is another way of representing an image. Each pixel, each element in this matrix is a double precision number. So we have a lot of precision with each of the pixel values in this representation of the image. The disadvantage is that such an image requires much more memory. The double precision numbers occupy 8 bytes of storage. The uint8 occupies only 1 byte of storage. So this image on the right hand side occupies 8 times more memory than the image on the left. And we can see that quite easily using the about function. Tell me about the variable im. We can see it occupies 1.1 megabytes of memory in the computer. Let's have a look at the other image, and you can see that it occupies 8.7 megabytes. But sometimes there are advantages in having the pixels represented by double precision numbers. In terms of the actual computer hardware, the double precision number is organized in memory like this. It occupies 8 bytes of computer memory, or a total of 64 bits. And the first bit is the sign bit, and that has got a value of 0 for a positive number, 1 for a negative number. That's followed by 11 exponent bits and 52 fraction bits, and I'll talk about those in a moment. This particular layout is defined by the IEEE 754 standard. So floating point numbers on almost all computers today are represented in this particular fashion. Now, if we denote the fraction part by F and the exponent part by E, the actual value that's represented is F times 2 to the E. So the E is the exponent part and F is we call it the fraction part, sometimes also called the mantissa. Now, the exponent has got a range of minus 1022 to plus 1021. If we do the conversion from binary into decimal, we see that this gives us a range, this multiplication factor, which goes from 10 to the minus 300 to almost 10 to the 300. So this kind of number has got an enormous dynamic range. Now, the exponent is represented by 11 bits that has got 2048 possible different values. 4 of those values are reserved, they're special, and one of them is used to represent an infinite number, another is used to represent a negative infinite number, one is used to represent what's called not a number, so that is something that is numerically invalid, and another value is used to represent the precise value of 0. The fraction is organized so that it is always in the range from 0.5 to 1. So the most significant bit in the fraction represents 2 to the minus 2, or 1/4. The least significant bit has got an equivalent value of about 10 to the minus 16. So that means that this double precision representation has got effectively 16 significant digits. So a lot of numeric precision and a very, very large dynamic range. That's the advantage of this double precision floating point representation of numbers within a computer. Now, there are some limits to the precision, and if we consider a number like this, 0.1, that's a tenth in decimal, it doesn't have a precise representation as a binary fraction. It is a repeating fraction in binary, so we can't represent it precisely. An example of this is, for instance, I want to look at the decimal value 90.1, and I tell MATLAB to display this in its long format, so that's showing a lot of decimal digits. And what we see is that 90.1 is actually represented internally by 90.09999, and the last digit is shown as 4. So it's wrong in the 17th significant digit. But as we just talked about a moment ago, double precision guarantees you around 16 significant figures, so this is to be expected. So to recap the numeric ranges of these different representations that we use for pixels, we can represent pixels as either unsigned 8-bit integers, which occupy a single byte of computer memory each, and they have a numeric range between 0 and 255, or we can represent them as double precision floating point numbers. They occupy 8 bytes of computer storage each, and we typically map pixel intensities into the range 0 to 1, 0 being dark, 1 being bright. There are also some difficulties when we use integer arithmetic. One of the problems is saturation, so if the result of an arithmetic operation exceeds the maximum possible value for that representation, it is clipped or limited to the maximum possible value for the representation. So in this case, the result of the arithmetic should be 300, but it's clipped to 255, which is the maximum possible value of a uint8 type. Another problem is quantization. So if we look at these two divisions, 49 divided by 100 gives a result of 0. It is effectively rounded down to 0, whereas 50 divided by 100 is rounded up to 1.